So thanks everyone to coming to the talk on our paper Sequential Information Design, Markov Persuasion Process, and its efficient reinforcement learning. So my name is Jibang, and this is joint work with Zixuan, Zhaoran, Zhuoran, Michael Jordan, and Haifeng. So let me start by giving you a motivation of this problem, sequential information design. And let's start with the most basic real-world problem that we want to apply, the standard information design, where you are a ride-sharing platform and there's a rider wants to request a pickup from a remote area. So in this problem, there's misaligned objective where this driver wants to get good tips for this long-distance pickup. And the platform instead wants to maximize the social welfare. So in this case, suppose you want to maximize the probability of this rider being picked up. And then there's information asymmetry in this case, where this platform knows the rider's history, whether he is a good tipper or a bad tipper, but the driver only knows the general rider type distribution. And the goal for the platform is that you want to exploit the information advantage so that he can maximize the probability of the rider being picked up. So how can we exploit the information advantage? So consider a very simple setup. This probability of rider being good tipper is 1/3, being bad tipper is 2/3, and accepting good tip is has utility 1, accepting bad tipper has utility 0, and if he refuses to order, he will just have utility 1/2. So clearly, if you're a rational driver, you would accept order only if this rider is more likely to be a good tipper. So the naive strategy 1 is you can reveal no information to the driver. So then for the driver, all he knows is the prior. So which is always more likely to be a bad tipper. So he will never pick up the rider. Another strategy you might think of is you want to reveal full information to the driver. That is, the driver will know exactly the realization of the rider. And then in this case, in expectation, only 1/3 of the chance it's a good rider and the driver wants to pick up the rider. So can we improve this social welfare? So here comes the art of information design, that we can use partial revelation through information signaling scheme. In particular, we can design two a signal variable that is correlated to the randomness of the outcome, say good signal and bad signal. And more concretely, we can think of this good signal as displaying some banner to the driver's app saying that this trip has a good chance for tips. And then through this standard signaling scheme, we can construct this two signal by splitting the probability flow. And then when the driver receives the posterior of receives a good signal, the posterior is slightly better than 1/2, so that his best response is to always pick up the rider, and receive the bad signal, he will reject the order. And then in this case, we can improve the probability of a rider being picked up to roughly 2/3. But then, if we consider a slightly more complicated real-world problem, there's two locations in this ride-sharing problem. And suppose at the timestamp 1, in location A, we have a driver. In location B, we have a rider. And then at timestamp 2, there's rider 2 showing up in location A, the driver 2 showing up in location B. So myopic approach in this case would directly persuade the driver to move from location A to B and pick up the rider 1 at the time 1, and then persuade the driver 2 to move from location B to A and pick up rider 2. As you can see, there's some kind of inefficiency here because drivers and riders, they both have to sacrifice the extra travel or wait time. Therefore, in this problem, we want to consider the state transition where this driver supply and rider demand are affected by the decision of persuasion. And we also want to, as the platform, want to care about the cumulative utility, where this platform cares about his social welfare in the long run. Therefore, in this case, we can actually propose a better strategy here. So at time step 1, we just persuade the driver to stay at his location. And then in the next time step, as the rider shows up, we persuade the driver 1 to pick up his local rider, and persuade the driver 2 to pick up his local rider at B. And then in this case, only rider 1 and driver 1 would need to spend some extra wait time. And so our work in a nutshell is trying to understand how can we integrate this kind of planning thinking into information design. So then let me introduce our formal model of sequential information design, known as the Markov Persuasion process. So it starts from the basic Bayesian persuasion case, and then we introduce the Markov environment. In this case, the sender will be able to observe information from the environment, and then the receiver's action would affect this environment's transition. And we should note here that this model is a strict generalization of the Markov decision process. You might already know that in this case, this two-party of sender and receiver in Markov decision process are just a single centralized planner. So let's quickly recall this Markov decision process before I introduce this Markov persuasion process. So there's an environment and agent. He is able to observe the state from the environment at each step, and then take an action according to his policy. And then gets a reward based on the current state and the action he take. And then the state transition will be based on his action taken and the current state. And the agent wants to maximize his cumulative reward, that is taken expectation over the randomness of transition probability and his policy. So in Markov persuasion process, however, we now have two parties, the sender and receivers. And we have this environment containing two parts of information. One is a private part of information that we call as the outcome, omega. And the other part is the public part of information we call as the state. So we assume this sender has the information advantage that he can privately observe this outcome that's sampled from some prior mu. And the state, on the other hand, are observed by both the sender and the receiver. And we assume this outcome prior may be different at different time steps. For example, in the ride-sharing example, the rider type may be different at different time of the day. And for the sender's action, we model it, we introduce the revelation principle in this problem that we can think of this signaling policy that he recommends the best action for the receiver to take. And this corresponds to the ride-sharing example that we directly suggest, where this driver should pick up the rider based on the current supply and demand status, and as well as the realized rider type. So then the receiver would according to take the recommended action, and both the sender and receiver will receive their reward, and then the state transit to the next phase. So notice here we still have this misaligned objective where this sender and receiver has different utility, V and U. And those utility we assume are also depend on the supply and demand, as well as realize the rider type, and also what the exact action this driver takes. So we assume this receiver is myopic, where he only tries to maximize his reward based on the posterior given the sender signal. And then the sender, however, is farsighted. He wants to maximize the cumulative reward. So how can we figure out the optimal policy for this Markov persuasion process? It turns out that we can adopt the Bellman equation in Markov decision process to this Markov persuasion process as well. Specifically, we can introduce this Q function, the state action function, as well as the value function, that they are defined recursively based on each other. And this value function specifically will limit to the policy that is subject to the persuasiveness constraint. And then we can still solve this recursion using dynamic programming, starting from the final step V, which is 0. But in reality, we will face uncertainty in the environment. That is, we don't know exactly what are the parameters about the environment. So how can we, in this case, still ensure persuasiveness under uncertainty? And also, how can we explore the environment effectively subject to the persuasiveness? Therefore, we introduced this problem of online learning in Markov persuasion process, where this prior, this sender's utility, and the environment's transition probability are all unknown. And for each, so this is episodic. This is similar to the episodic Markov decision process. And for each episodic, we will execute a signaling policy and obtain some data, and then using this data to update the learning to update the learning algorithm. And then we will measure this learning performance through the regret. That is measured by the suboptimality of the executed policy versus the optimal policy we obtained from the Bellman equation. So how can we achieve a no regret algorithm? We introduce this reinforcement learning technique using optimism and pessimism principle. So in a nutshell, what we are doing here is that we want to have this learning sender to send a pessimistic information signal to guarantee that this signal is persuasive even in the worst case. And also, and so that this receiver will take an optimistic action that effectively explore the environment. So let's go to the detail. How can we ensure persuasiveness using pessimism? So the problem we are facing is that we have this empirical prior somewhere, and it's very likely different from the ground truth prior. And then we can do a uncertainty quantification about around this empirical prior, and so that this ground truth prior will be contained in this confidence region with high probability. And then we just define the signaling scheme that is persuasive to any possible prior inside this confidence region. So in this case, we can formulate our persuasive signaling scheme into the following format, where we have this additional constraint of satisfying all the priors inside this confidence ball. And it turns out that doing this kind of pessimistic persuasion, we will suffer a regret only linear to the distance between the empirical prior and the ground truth prior. And how can we achieve, how can we effectively explore those Markov state with good value? So in this case, we can also do uncertainty quantification on the Q value, and then set a Q value higher for those less explored state action pair. Specifically, we can construct this Q tilde function that is the standard empirical estimation of the Q function plus the confidence value of this Q function. And then in the end, we can obtain a regret of square root t, where this it has to the factor of squared to the 2/3 of the feature dimension, and also to the square of the episode length. So, and this additional square root to the edge term is due to the pessimism. So just to highlight a few technique we use here, that we depend on a tailored regret decomposition in order to decouple the optimism and pessimism. And then we think this design principle of optimistic and optimism and pessimism can be of potential use for other strategic learning problem, where you want to use this pessimism to satisfy the incentive constraint with high probability, and also want to use optimism to explore the environment effectively. So for the future work of this Markov persuasion process, we want to consider the setting where the sender have no knowledge about the receiver's utility. And also we want to design learning algorithm that has regret bound matching the sample complexity lower bound of learning in Markov persuasion process. So that's it for the talk. Thanks. Please check out our paper for more details.
Yeah, thanks, Jibang. So let's see whether we have time for a few questions.
At some point, you talked about choosing a policy that is persuasive no matter what the true prior is. How do you know that such a policy exists?
Sorry, say that again.
At some point, you talked about choosing a policy such that it is in the intersection of these persuasive sets. Like worst case assumption. Yeah, there.
I see.
How do you know that intersection is non-empty?
Yeah, that's not empty, because if you use a full information signaling policy, it must be persuasive.
Good. So next question.
Okay.
Yeah. So I guess the answer, yeah. Next question. Yes. Or you can ask, I so the question is about the last the future work on the last slides. Can you comment on how tight your regret bound is? What is the room for improvement?
Yeah, currently we don't have a regret bound proof specifically for Markov persuasion process, but our hypothesis is that it has this additional square root h term over this standard Markov decision process because of this persuasion you have to do under uncertainty. And you can see that our bound is still not tight over this D.
That answer. Good. Any other questions? Is there a question online? I don't see questions online.